So let's talk about public key cryptography. Specifically, we'll go over RSA, which stands for Rivest, Shamir, and Adelman, which are the three people that popularized this technique. RSA is a form of public key cryptography. Public key cryptography has a person that has a key that they keep to themselves. This is called a private key. And so Alice here is going to create a public key, and then she's going to create a private key. Now, her private key, she keeps to herself, but her public key gets published so that anyone can use it. So taking a look at the diagram, we're going to have that Alice is going to generate the keys, and then she's just going to post her public key somewhere online. There's some repository that people can use. And then later on, when Bob wants to encrypt a message, he's just going to look it up online. He's going to find that public key that belongs to Alice, and he's going to encrypt his message. And he's going to send that ciphertext over that channel that is insecure. He's going to send C. Alice is the only person that has that private key, so she is the only person that's going to be able to decrypt M. As before, we have that eavesdropper in the center, but again, all they can see is the ciphertext, and they do not have access to the private key. They can see the public key, so they can encrypt all they want, so because anyone can encrypt, but they cannot figure out anything about the ciphertext, as we saw before. The main difference here from public key cryptography compared to what we talked about with private key cryptography is that now there is this imbalance between the parties where Alice has a key that other people don't have, and that's what she's going to use to decrypt messages. And when Bob is encrypting a message, it's specifically being sent for Alice. He has to pick the key that belongs to her for her to be able to use it. And so with that, I do want to talk about what RSA is, and we'll talk about the three-tuple of key generation, encryption, and decryption. But before we can go into that, there's a little bit of review that we need to have to be able to understand what the steps of key generation, encryption, and decryption are. The first thing that I would like to talk about is modular exponentiation. We've talked already about how A plus B mod n is equivalent to A mod n plus B mod n. Remembering to do that mod n on the outside there. And we also have that A times B mod n is equivalent to A mod n times B mod n, all modded by n. And so if you take this multiplication rule and think about the fact that A to the k is just multiplying A by itself k many times, then A to the k mod n, you can move that exponent around. And the other thing that's really helpful here is the fact that we can rewrite our exponents. So if I have a k, I can break it up into some sum, k1, k2, all the way up to kl, and I can say A to the k is A to the k1 plus k2 up to kl, and addition in the exponent is equivalent to multiplication in the base. The other thing I'd like you to remember about is Fermat's little theorem, and the way that I've written it here is for any prime p and for any m and z, if m does not divide p, then m to the p minus 1 is equivalent to 1 mod p. Right, so those are some rules that we've seen before. They are actually going to be put into use now. The next thing I'd like to talk about is Euler's phi function. Now this is new. The phi function is the number of positive integers less than n that are coprime to n. And so recall that the definition of coprime is two numbers are coprime if their GCD is 1, because they have no factors in common. GCD is the greatest common divisor. Let's talk about the numbers that are less than n that are coprime to n. If I have the number 4, I can think about all the numbers that you can get when you mod by 4, which is 0, 1, 2, and 3. But of course, this definition asks us to look at positive integers, so I'm always just going to kick out 0. I'm only going to look at 1, 2, 3. So these are the positive integers less than that number. And now I want to see what numbers are coprime to n. So I have GCD of 1 and 4, GCD of 2 and 4, and GCD of 3 and 4. Well, the GCD of 1 and 4 is 1, but the GCD of 2 and 4 is 2. And the GCD of 3 and 4 is 1. So here, thinking about that, I have 1, I have 1. So of the 3 numbers I had left, 2 of them are coprime, and I can conclude phi of 4 is 2. So I'm counting here. Let's look at one more example. So again, thinking about those numbers less than 5, 1, 2, 3, 4, and of course, I always kick out 0. And then thinking about the GCD of each one of them. Phi of 5 is equal to 4. One of the reasons we can conclude that is 5 is prime. And so all of the numbers less than it, positive numbers that are less than it, are going to be coprime. In fact, in general, we have a lemma which says 5p is equal to p minus 1 for all primes p. Since p is prime, all integers smaller than p must be coprime to p. The only integers that are not coprime to p have p as a factor, and that's not possible if you have integers that are less than p. So looking at some examples here, we just saw phi of 5 is equal to 4. We could do phi of 2, and so phi of 2 is just going to be 1. The only number that is coprime to 2 that's a positive integer is in fact 1. And we can do that same thing with a couple of other primes. And so what I always like to do, I just write out those numbers that are less than that number, and coprime, I always kick out the 0, and I am left with the numbers that are coprime. Now we have another lemma which says if I have a number that is composite but is the product of 2 primes, then phi of p times q is going to be phi of p times phi of q. So p and q are primes. My number is going to be p times q. Its Euler phi function is going to be phi of p times phi of q. Let's look at an example. So here I have 14. 14 is equal to 2 times 7. And so I break that up into phi of 2 times phi of 7 because 2 is prime and 7 is prime. And phi of 2 is 1 and phi of 7 is 6. So I will get 6. And let's go through my normal system for doing this, where I write down all of the numbers that I have mod 14, which is 0 through 13. And then I think about what numbers I'm going to kick out. Well, I always kick out 0, and I'm going to kick out all the even numbers, which is 2, 4, 6, 8, 10, and 12. And so I am left with some other numbers. I need to go through and kick out 7 as well, because phi of 14 is phi of 2 times 7. So I also have to consider phi of 7. At that, the numbers that I am left with are 1, 3, 5, 9, 11, and 13. And so if I count those up, 1, 2, 3, 4, 5, 6, I will get that the cardinality of this set is 6, which is exactly what I got when I did the lemma 2 application on phi of 14. So with that, let's look at this Euler's theorem. If I have a, n, and x, and a and n are coprime, then I have a to the phi of n times x mod n is equal to 1. And so this should look somewhat reminiscent of Fermat's little theorem, where we said m to the p minus 1 is equivalent to 1 mod p. And then we did have that m does not divide p for this. And so this actually looks very similar. In fact, because I have p minus 1 here, this is the same rule. Phi of n would be p minus 1 if I replace those values. We're not going to prove this, but we are going to show an example. Let's pick a is equal to 5, n is equal to 12, and x is equal to 2. And so first of all, looking back at the theorem, I need a and n to be coprime, so GCD of a and n is equal to GCD of 5 and 12. And yes, those are coprime. Okay, so now the next thing we want to do is calculate phi of n. And phi of n in this case is going to be phi of 12. And phi of 12 is going to be 4. Let's talk about this just for a second, because 12 is 3 times 4, or 3 times 2 times 2. But that same rule that we did with lemma 2 is not going to apply because I have 2 factors in common. So I'm just going to have to count these out. I know to just look at all the numbers. Less than 12. And then I know to go through and kick out anything that is even. 4, 6, 8, 10. And I know to kick out anything that's a multiple of 3. So that's 3 and 9. And that leaves me with, let's see, 1, 5, 7, and 11. And so I would have to conclude that phi of 12 is 4. So let's go through with a to the phi of n times x mod n. This is equal to 5 to the 2 times 4 mod 12. And we can rewrite this. This is 5 squared to the 4 mod 12. And one thing you want to be careful of here is use that triple equals, because these are congruent, not equal, congruent. 5 squared is 25, which I know is equivalent to 1 mod 12 because it's 24 plus 1. And that is in fact equivalent to 1 mod 12, which was what we wanted. All right, the next thing that I want to give is this proposition, which is, it's like a theorem. P and Q are distinct primes. I have these two values, E and D, and E and D are between P minus 1, Q minus 1. So another way to write that would be 5P times Q. And then I have this rule here where E times D is equivalent to 1 mod P minus 1, Q minus 1. In other words, E times D is equivalent to 1 mod phi of P, Q. Now, for every m, we have that m to the ed is equivalent to m mod pq. So with that, we now have all the building blocks for RSA. The first thing that we are going to have is keygen. All right, remembering that we have keygen, encryption, and decryption. With the things that we learned with modular arithmetic, we can use those to figure out what our scheme is going to be. So with keygen, we're going to have 2 prime numbers that we pick. And here I want to pick really large number. It's several hundreds digits long. Right? So when we do examples, I give you something like P is equal to 43, but here P is really large. It's hundreds of digits long. We're going to compute n is equal to P times Q, and we are going to find this positive integer e that is co-prime to P minus 1, Q minus 1. And so just keeping in mind, Alice is the person that is going to be creating keygen. And then what she's going to do is she is going to post NE as the public. It is hard computationally to find the prime factors of n. That's how we use this public-private key system, because nobody can really factor those numbers. Even though Alice publishes N, nobody can figure out what P and Q are easily. Bob has N and E that he learned from Alice, and he has a message in mind that he wants to encrypt. So all he's going to do is he's going to take his message, make sure that it's an integer where N is greater than M, and he is going to do M to the E mod N. Alice is the only one with the private key, and so the private key here is just PQ that she picked herself, right? She can also calculate D. She can find that D such that D times E is equivalent to 1 mod P minus 1 times Q minus 1. And she can compute then C to the D mod M. Let's check for correctness real quick. So C is equivalent to M to the E mod N. And then I'm going to do C to the D mod N as Alice. C can be replaced by ME. And then I have ME to the ED, E times D, mod N. Looking back up at our rule, M to the E times D is equivalent to M mod PQ. So when I go back here, I have ME to the ED mod PQ, which is in fact equivalent to M, based on that proposition. And so Alice here is in fact going to learn the message.